Hello, my name is Evan. I'm going to show you guys how to do assignment number 4, steganography today. So the first thing, as with any assignment, is you should really read the assignment page. That's really how you're going to know what you need to do. So there's some stuff up here which we can kind of ignore, especially ignore this. This is what we really want to do. We want to see what classes we're going to be writing and what should be in them. So we're going to write a steganography class with static methods, 2 new exceptions, and a main driver, which is pretty standard across all of our projects. Looks like here he has shown us what our exceptions are going to be, not enough space exception and secret message exception. And then we've got our steganography class down here, which will have these 3 methods in it. getDataLocations, decode message, and then encode message. So that's generally what we need to do, but how are we going to do that? That's where the intro comes in. Basically, steganography means hiding messages in plain sight, and what that means for us is we're going to be putting sort of random bytes into a WAV file, which is an audio file, and the bytes are going to correspond to certain primitive types in Java, integers and characters, that only our program will be able to read back out of them. Somebody without the knowledge of how this sort of encoding scheme works won't be able to read the message, which is what makes steganography so kind of cool and powerful. So before we even write any code, I just want to go through and see sort of how this schema works. We've been provided down here with 2 different audio files. This one actually has a secret message in it, and even though it's relatively confusing, this one doesn't. This is just a plain old audio file. So the first thing we're going to do is I'm going to download this file, save file, and I'm going to actually open this file in a binary sort of data viewer. The one that I have is called iHex. And it basically, this kind of program allows you to open up binary files, and it'll show you a hexadecimal representation of what's in them on one side, and it'll try and convert them to ASCII or UTF-8 or something over here on the left. So what we're going to do is I'm going to open up my WAV file here in iHex. It should be in downloads. And alright, so we've got it open. You can see all the hexadecimal over here. There's quite a few bytes, and then we're going to be, there's the UTF-8 representation over here. So the first thing that we need to look at is we need to see how our schema works. So basically, there is a header, which is 50 bytes. There is an integer, which is 4 bytes. And then there's a character, which is the first letter of the message. And then after the character, which is the character is 2 bytes, after that character, the next 4 bytes is the index of the next integer. So this first, 54 to 4, so 50, around 62 bytes, I think. I'm probably doing my math wrong. This first number of bytes will be standard in every one of the files that we make. There will always be this 50-byte header, then there will always be a 4-byte integer, a 2-byte character, and another 4 bytes for the next character's location. So we should be able to go into this encoded file, and we should be able to find those things in here. What the hexadecimal viewer allows us to do is parse through the bytes of the WAV file and sort of look at their hexadecimal values and their binary values, and then we can convert those values into integers and characters as we need. So I'm going to turn off override mode here because I don't need to override, I can read only. Alright, so the first 50 bytes of our file should be a header. So you can see here it says 0 bytes, and when I click it shows 5 bytes. So I'm just going to click until I get to about the 50th byte. So it looks like I'm also going to use my arrow keys. And okay, here's our 50th byte. So all of the text here, this is all of the WAV header. You can see it says WAV, RIFF2, WAV FMT, so WAV FMT means format, and then you can see it says data. So those are, this is the header, these 50 bytes. We're not going to do anything with this, and we especially don't want to touch this with our program because then the WAV file won't work. But as our schema sort of shows us, the next 4 bytes, because an integer is 4 bytes, should be the length of the message. And so you can see this is the 50th byte, so the next highlighted byte is the 51st byte, the 52nd byte, the 53rd byte, and the 54th byte. So these are our 4 bytes, and you can see over here it doesn't show anything because these 4 bytes don't mean anything in ASCII or in UTF-8, whatever the encoding is. I think it's Mac Roman, so it's basically, I think it's the UTF-8. Not sure what the difference is, but it doesn't really matter. Now, what we do want to know is we want to know, since this is an integer, we want to know what the integer value of this is. And so what we can actually do is here in my program iHex, if you go to unsigned integer and then you go to big endian, this number changes. It actually becomes 32, and that is the length of the message. If we read it into, if we were to write our program and read this first byte into memory as an integer, we would get 32. The only reason we need to use unsigned integer in big is because in Java the primitive integer is unsigned and it uses big endian. And what those mean is sort of outside the scope of this video. You can go Google them if you need to, but basically what's going on is these first 4 bytes are an integer, and we can see that that integer equals 32. So now what we should do next is look at the next section of bytes. The next bytes after the first 4 should be a character, 2 bytes, and we can actually, so this is a 54th byte, we can select the next 2 bytes, and we see 2 bytes selected out of 54. We can see over here there is an I, capital I that's been selected, and then there's there's 2 empty bits here. Now this is actually pretty important and it's mentioned in part of the assignment. If you go down here, it says see the notes below why Java thinks you should waste 2 bytes on a character. So basically what happens is Java uses for character encoding, instead of using what is called UTF-8, which uses 8 bits or 1 byte. The Java decided that its characters would be written in UTF-16, which means it uses 16 bits or 2 bytes. So that's what that's why a character is 2 bytes. UTF-16 just means you can fit in a lot more characters, but for the Latin alphabet, they still fit into 1 byte. So we can see here this is just an empty byte, but the 49 here, the second byte, is the sort of base byte. There's a proper name for it, I'm not sure what it is, but basically this is an empty byte, and then this is 49, and you can see that that actually corresponds to the letter I. So this is the first letter of our message is I. So I'm going to actually open up Atom or Eclipse, and we can sort of keep track of that. So while that's opening, so we know that these 4 bytes are our first character. And then if we look at our assignment again, or our schema, we should call it, we can see that the next 4 bytes are going to be the index of the next integer. So going off of this, this is the 55th byte, that's the 56th byte. The next 4 bytes should be the integer for the integer location of our next character. So 1, 2, 3, 4. If you look down here, it says 102676. So at the 102,676th byte should be the next character of our message. And well, my computer is chugging. Anyway, yeah, the next character should be at 102,676 bytes. So we can actually scroll all the way down there and find it. So I'm not gonna select anything, but if we look at the numbers here on the side, we can see which byte number it is. And so let's see, 102,676. Skipped over it. 100, 102, 102. Oh wait, this is 10,000. Never mind. All right, I got a lot more scrolling to do. And there we go. 102,676. All right, so this is probably as close as we're going to get, but I just remember 102,676. So now we can look here at the bottom. there, this is the byte where the next character should be. So again, let's select the next two characters, and you can see over here there's an N. So the next letter of our message is N. So I'm going to go over to Eclipse and just write these things down. I'm going to make my project right now. I'll call it Steganography. And I'll just hold a text file in this project so we can keep track of what our message is. All right, text file. So we've got an I and then a lowercase n. All right, so let's do this a few more times, and we can really see what maybe the first word of our message is. So again, following the schema, once you see a letter, the next 4 bytes are always the location of the next letter. So this was our letter, lowercase n. So let's select the next 4 bytes, and you can see it says 205298. So let's scroll all the way down there. It's another 100,000 bytes down. 205, 205, 298, 205, 296. All right, 205, 298. All right, so this is the 200,000th byte or so. These 4 bytes should be our next letter. So it's a T. So we can go over to Eclipse, and that's a little T. And then the next location of our next letter should be 1234, 307920. All right, let's scroll all the way down there. So we're just scrolling to the 300,000th byte about, and we're going to look at what our character and where our next letter are. So 307. 920, 920. Hey, there we go. All right, so this is the 300,000th byte or so, and you can see we've got another 4 bytes. One is empty, the next is full. It's got a value in it, and you can see over here it's got the value of R. So this is our next letter is R. So INTR. This is looking like a familiar word, but we'll go to the next character anyway. 1, 2, 3, 4. Our next character is at 400,000 bytes or so, so let's scroll down again. 410, 542. 410, 410, 544. So our next character is going to be around here. 410, 542. All right. 1, 2, this is our next character. It's an O. So you can see the first word in our message is intro, and so you can tell we're on the right track because that's a real word, and we've been getting relatively reasonable numbers out of looking at the locations of the next integer. They're all separated by about 100,000 bytes, so it makes sense that these have been placed logically rather than just being random bytes. If I select some other bytes, like these 4, it says 4,700, which wouldn't make sense for a location, and it also, you can see over here, there are all kinds of different characters that are being shown because, well, it just so happens that these 4 bytes correspond to these 2 characters, but they're not actually part of our message. So it's really important that when we go through, we understand and we can check that 2 bytes are a character, and then the next 4 bytes are a location that makes sense within the parameters of our program. You can see this number is obviously not inside the parameters of our program. It's what? 1,963,000,000. We don't have that many bytes in this WAV file, so that's obviously not the location of our next character, so we really don't need to worry about that. All right, so now that we've gone through the how the message should actually work on a binary level, we can start looking at how to write this in Java. So I'm going to go over to my Steganography project, and I'm going to create the 3 classes that were specified. So we've got our 4 classes. Sorry, the Steganography class, the 2 exceptions, and the driver. So let's just do that really fast. Driver static comments, and then we'll also have our Steganography class. Whoops, I don't want to run it. I want to create a new class. Steganography. It doesn't need a void method, so we'll just skip that. And then our two exceptions. So for our exceptions, we can actually do something pretty, we can make this pretty easy on ourselves. Instead of writing public class, whatever exception extends exception, we can just write exception in here. So java.lang.exception, and then we can write our not enough space exception. And we can generate comments. We have the option to inherit abstract methods, but Eclipse will insert all these methods that we don't really need, so we don't need to click that checkbox. So we should just get an empty exception, and I'll just put in a basic constructor for it. Now, if we look at the specification for this exception, it says that its message should indicate how much space was needed and how much space is available. It should contain one constructor that takes the size information as parameters and calls the exception constructor to set the message appropriately. So whenever you create an exception, the argument to the constructor is always a string that is the method, or excuse me, that is the message of the exception. So here we want to take two integers. We need int space needed and int space available. So those are the two parameters that have been specified for us, and then we need to use those to craft sort of a message exception. And so what I'm going to do is I'm going to call the super constructor, which is the exception constructor, and as I just said, the parameter for the super constructor, or for the constructor for an exception, is always a string, which is the message for the exception. So I'm just going to write my message in here using the two integers that I've been given, and that will be the message for our not enough space exception. So we're going to write space needed plus space, and I believe these will be in bytes, so I'll just write bytes were needed, but plus space. And but only. So this is just the method that, or this is the message that will be shown if we throw a not enough space exception. And I'm going to write whatever the fuck this is supposed to be, serial. So that's just supposed to make this not yellow anymore. Because that's annoying. All right, so then we need to create our secret message exception. And this can also inherit from exception. And it doesn't need any of those things. And so for this one, it's just if there's an error decoding the message. There's nothing more, it doesn't have anything really specific, so we're just going to sort of copy the exception constructor. And that's really about it. That's all that our exception classes are going to do. All right. So now that we've got all of our classes created, let's look at the Steganography class where we're going to be doing most of our work. It lists these three methods in order, and I'm going to say that we do write them in that order because the first one is the easiest to write, and it helps us the most if we can see how to decode a message before we encode the message. So first we're going to write getDataLocations. This is a static method that returns an array of integers and takes a start value, a stop value, and a number of locations, and it throws this not enough space exception. So let's just sort of start writing that in our Steganography class. And then of course we need the throws. So now that we've got the sort of frame for our method, getDataLocations, we need to think about what it's going to do. So here it gives a good description. Returns an array that indicates where each character in the message should be stored. So basically that's what this integer array is it's going to be an array of integers which are the locations in memory or rather in the bytes of our file where we're going to be putting integers. So that was like the location of our I, the location of our N, the location of our T, etc. And it's easy to sort of compute the locations because we just need to sort of divide them up. So first of all, we need to see how long our message is going to be, and we know that sort of each packet of information from our schema, each little packet that we're going to put in is going to be 4 plus 2 bytes. It's going to be 6 bytes long, which is going to be our character and then the index of our next character. So I'll just write that in as int standard length or something, so we can hold that. So this is going to be the size, or instead of calling it length, let's call it size. Character, I don't know, package size. Anyway, so yeah, each little blip of data inside of our file is 6 bytes long, and if we have our number of locations, we know how many. We know how many packages there's going to be. So we're going to say total size is number of locations times package size. So this shows us how much space all of our packets or packages are going to be taking up inside the file. And what's important is we need to know how much space is between these two values, the start and the stop values. So we'll say int space provided equals stop minus start, because stop will always be greater than start. And then we want to see if the total size of our message is greater than the space that's being provided between these two values. That's when we're going to throw our not enough space exception. So we're going to write if total size greater than space provided, then we're going to throw not enough space exception. And if you remember, our two parameters for this were the space needed and the space available. So the space needed is the total size, and the space available is space provided. So now that we've done that, what do you want? Not enough space exception. Oh, throw new. Whoops. All right. So now it should get it. All right. So now that we've handled that case, next we need to go on to constructing this integer array. And so the first thing that we need to know is how long is it going to be, because when we type int locations, we need new int, we need a number to put in here. And actually it's really convenient, because how big the locations array is going to be is actually just the number of locations. So we can put num locations in here. Locations, I hope I spelled that right. And the next thing we need to do is basically if we want to iterate over the size of the space we're given, and we want to sort of divide it up into parts. So we can say that if this is how big our package is going to be total, then how much space is going to be between each of the packets is space provided divided by total size. So that we want to be an int as well. So we'll just say int buffer amount, because this is literally the amount of space between each packet. So we're going to say space provided divided by total size. And this will round to an integer, so we don't need to worry about being off by half of a byte or whatever. Now the next thing we need to do is we're going to say we need to think about how our schema works. So again, at the header, the first thing that's going to happen is we're going to have the length of our message and then our first letter. So we can actually include this first letter and index of next int in our integer array. We just need to make sure that it's appropriately offset. So again, if this integer is 4 bytes, then our first letter is always going to be at location 54. So we can say locations 0 equals 54, because that will always be the location of the first character. And then what we need to do is we need to go through our array and increment our location by the buffer amount for every location that we have. So we can just use a for loop to do that. We could have written locations.length here, but they are literally the same. It's not going to change. We don't need to worry about using that, so we can just use num locations. Then what we're going to do is, actually what I'm going to do is I'm going to say starting location. Instead of assigning this location right now, I'm going to create an integer called starting location. And we're going to say that locations I equals starting location. And then before we go to the next iteration, we're going to add the buffer amount to the starting location. So what this should do is it should iterate over each value in the locations array and increase the starting location amount by the buffer amount, and that should evenly space our message throughout the size of the file. And now that locations has sort of been filled out, we should be able to return it, and that will be that's the end of writing our getDataLocations method.